So up to this point, we've been talking mostly about quadratic equations in standard form, where everything has been distributed and multiplied out, and all the like terms have been combined. But as we started talking about factoring, we began to see quadratic equations in essentially the polar opposite format, where everything had been undistributed as much as possible. Everything had been factored as much as possible. And a quadratic expression that has been factored as much as possible is said to be in factored form if it is written in the form number out in front, x minus some number, and it's traditional to call this number R1, and maybe something in the back, R2 in the back, x minus R2. So just as a quick example to make this concrete, something like 2x minus 1, x plus 4 would work. A would be taking the role of 2 here, and rather than x take away R1, our second factor has x take away 1. And so that's taking the role of R1. Now the back of this may look a little bit sketchy at first because it doesn't have a subtraction here. But we can alter this slightly so that we can see the subtraction hidden in this factor. Instead of x plus 4, I'm going to rewrite this as x minus something else. What do you think? If this is going to be written as x minus something, what would it be? Now remember, when you subtract a negative number, that's the same thing as adding the positive version of that number. So x plus 4 is the same thing as x minus negative 4. And that means that R2, the second number here, is the opposite of plus 4. It's negative 4. And so those would be the three constants in factored form. For this particular example, leading coefficient 2, first number 1, second number negative 4. Now, just like standard form, factored form has its own unique advantages. When we had standard form, there were two graphical features that we could see without doing any calculations whatsoever. For standard form, we could tell whether the parabola opened up or down, and we could see what the y-intercept was. We could just read those without doing any work. Now, I claim that if you're in factored form, you can also detect, without any calculations, whether the parabola opens up or down. Whether it opens up or down. And the secret is that this A, this number in front in factored form, is actually exactly the same A that you see show up in standard form. They're the same number, and that's why I am allowed to call them the same letter. They're actually exactly the same. So in factored form as well, all I have to do is look at the number out in front here, look at the A value, and I can determine if A is positive, the parabola opens up. If A is negative, the parabola opens down, smiley or frowny. Now, when we had a quadratic equation and it was in standard form, we could detect the y-intercept without doing any work at all. In factored form, the opposite is true. You can detect the x-intercepts without doing any work at all. And that comes from the fact that if you go into this equation and you set y equal to 0, you are in the prime position to use zero product property. Let's see it in a concrete way, as applied to our running example in the back. Say I have 0 equals 2, x minus 1, x plus 4. Zero product property says that if you want this to happen, there are really only two possibilities. The first factor will never be 0, but the second factor would be 0 so long as x is positive 1, so long as x is equal to R1. And the factor in the back would be 0 if only x were negative 4, if only x were equal to R2. And this is true in general. The x-intercepts from factored form will always be equal to this R1 and this R2. You can read them directly out of the equation, the R1 and the R2 in the equation. Now, because the x-intercepts can be obtained without any calculations at all, it would be nice if there were a way to calculate the x of the vertex using those x-intercepts, because they're so easy to find. And here's the key principle. I'm going to do my level best to accurately sketch a parabola over here. Here's the vertex, and the graph cascades down symmetrically from that point. Because the parabola has a symmetry at the vertex, the x-intercepts are evenly spaced away from the vertex. Or put another way, the vertex is directly between the x-intercepts. So if you want to know the horizontal position of the vertex, all you have to do is find the number which is directly in between the two intercepts. Maybe this is 1 and negative 4. What number is directly between those? You may recall that if you want to find the number which is directly between two other numbers, you can take those numbers and average them. Average them to go directly between the x-intercepts. Now, once you've gotten the x-coordinate of the vertex, the y-coordinate of the vertex comes quite cheaply. As always, just plug in xv to determine yv. Now, let me make it concrete with a short example. Let's get this one that we have been doing up to this point, 2x minus 1, x plus 4, where we found that the x-intercepts were located at 1. Let me actually call them r's. X-intercepts were located at 1 and negative 4. So if I want to know where, horizontally speaking, the vertex is located, I can just take those two numbers, add them together, and split the difference. xv is equal to negative 3 over 2, or negative 1.5 if you prefer. And then if I want yv, all I have to do is plug that number, negative 1.5 minus 1, plug that number into this formula. I'll leave the calculations to you, but this is how I would find the vertex in this particular situation. Find the x-intercepts, just read them out, average those two numbers to get xv, plug that into the equation to get yv. Now, if you are ready to think about the vertex from that perspective, then you can get some traction on more abstract problems like this one. So you have a company selling some piece of technology. Let's just call it a gizmo, selling gizmos. And suppose that the money that the company brings in, called its revenue, the amount of money the company makes, suppose that that is a quadratic function of how much they charge. Now, to me, that's not too outrageous. Charge versus income. Because if you are selling something and that's your only way of making money, and if you don't charge anything at all, if you're just giving your stuff away for free, if you're giving your stuff away for free, you're not making any money as a result of that. But if you charge an enormous amount of money for the stuff that you're selling, no one's going to buy it. And no one buys what you're selling, you're not going to make any income in that case either. So somewhere between these two extremes, giving your stuff away for free and charging so much that no one wants to buy it, somewhere in between these extremes is the sweet spot, where you're charging just enough to get as much money as possible. Now they have done some research here, and they found that, okay, if you don't charge anything for your gizmos, if you charge $0, okay, you're not going to get any money from that. And the extreme end is if you charge $1,000 for the gizmos, no one's going to buy that in that case either. It's too expensive. So how much should they charge for one gizmo? How much should they charge to get as much money as possible to maximize the revenue? Maximize. So it's signaling to me vertex, vertex. Well, the vertex is located directly between these two extremes, a number directly between 0 and 1,000, directly between 500. If I want to make as much money as possible, I should charge $500 directly between these two x-intercepts.